All right, welcome back. Let's continue with our class. So in the second lecture, we are going to continue with the pruning. We are first going to talk about determine how to determine the pruning ratio. Essentially, we want to determine what the target sparsity should be for each layer. So finding for, give you a specific network, we have many layers. So we need to determine like what is the prunation, what is the best pruning ratio for each layer, since different layer have different sensitivity, right? So some layers are more sensitive to pruning, some layers are not. But how do we find it out? So the most intuitive way is to do this so-called sensitivity analysis to determine the player pruning ratio. So let me show you how does that work. So if you look at this figure over here, the x-axis shows the pruning rate, the y-axis shows the accuracy. And for layer zero, okay, and we just do this, keep everything unchanged, but just the pruning ratio for this particular layer. So what we have is that you can see that when you are keeping, if you keep prune this particular layer, you will plot this, this line here. And then you just keep plotting this line for different layers, like layer one, layer three, two, three, four, five, until you plot like this chart for all the layers. So this one just tells you uh, how sensitive each layer it is. If you look at this chart, just before we do anything, if you just look at charts that, like, if we just simply pruning each layer to 40%, you can see that like the accuracy rarely the accuracy rarely drops. Okay, um, it's we pretty much like maintain the original accuracy for each layer. Um, and then like if you go further, then you start to see accuracy drop. So you can see that different layer have different sensitivity. For the green line, the L1, you can see it's less sensitive. It means that like even if I prune more, the accuracy is still not dropping, right? So whereas the blue line, it's much more sensitive. You prune like 50%, it start to see drop. If you prune all the way to to 80 to 90%, it drops like significantly. So that just tells you the sensitivity of different layers. So usually, like if we want to find a perfect pruning ratio for each layer, what we do is that like we set a target accuracy, right? A target accuracy threshold, like this. And then like you see, wow, if we want to achieve this, the blue line you can't prune more than 70%. For the green line, you can prune more than 90%. So in this way, we determine the pruning ratio for different layers. Um, is this optimal? It's not, maybe not, because there's one thing that we haven't considered is the interaction between layer. So far, we have been, doing this sensitivity analysis just independently, right? So we freeze all the other layers when we are analyze the sensitivity of one particular layer. Um, but then, apparently this may not be the optimal solution. So how can we, go further? So this automating pruning, there's a paper called AMC, um, um, automatic model compression, AMC. So what this paper want to do is this automatic pruning. It want to automatically learn what is the pruning ratio for each layer. So giving a overall compression ratio, how do we choose the layer pruning ratio? So the sensitivity analysis ignores interaction between the layers. Therefore, it's suboptimal. So what it wants is that it wants to have a automatic process to choose the pruning ratio for each particular layer. Okay, and this is the overview of this method. And let's take what it is. This is a method based on reinforcement learning. So what the reinforcement learning does is that it has a critique and has a actor. Okay, and it has this embedding, and it uses DTPG. It's a reinforcement learning algorithm which can output a continuous decision. So what it does on the high level is this. So the actor will constantly choosing the pruning ratio, the channel pruning ratio for each particular layer. Okay, and this pruning ratio can start from ranging from 0 to 1, and it can be any arbitrary floating point number. And that's why we call this is a continuous operation, because the selection of the pruning ratio is a continuous range. It's not like a discrete number. Okay, so once the actor selecting a pruning ratio, and then you are going to train the model, and you are so we are going to train this model. We are going to change the model and get the arrow. Like we want to see if the arrow actually goes up or goes down, right? And use that as a reward. So the reward equals to a negative arrow. What that means is that we want to minimize the arrow, so to maximize the reward, right? So the critique is going to use the reward to guide the selection of the embedding. So the embedding essentially is a number of channels, the and all that, the kernel size, the height and weights, and all that parameters. And then the actor just keep searching the parameter, the pruning ratios, and the critique is keep using the reward to guide the search of this pruning ratio. Sometimes we can also add this flop into this reward. What does that mean? If you want to maximize the reward, apparently you need to minimize the arrow. Also, you need to minimize the flop. So the flop means that like the number of operations, right? The floating point operations per second. So in this way, essentially, if we are doing this, this equation is guiding the search process to minimize the arrow and also minimize the number of parameters or the max. Okay, so we want to minimize the latency as well as the accuracy simultaneously. This is the formal definition of this AMC. The state is 11 features, including the layer indices, channel numbers, kernel size, flops. The action is a continuous number, which is a pruning ratio for each layer. This agent using DTPG algorithm. If you don't know it, please there are a lot of videos on explaining this TTPG algorithm. I don't think we are going to explain reinforcement learning a lot. But if you really don't understand, you can always check with me. And then we have this reward function, which is satisfy the constraint. If it says constraint equals negative arrow, if not, it's this. And you can also optimize the latency by adding another term into this reward. And this shows the result. The human designed prune for ResNet 50. The density is this, and the AutoML can find a smaller network essentially. And this figure, the x-axis shows the layer index, like which layer of this ResNet 50. So totally 50 layers, okay? And the y-axis shows the density. So the green line, yellow line, the blue, orange, green, red, these are, the algorithm have multiple stages. And finally, it converges after, stage 4. So what we find out, what this figure is trying to show is that we only need to look at the red line here, okay? Because that's the final result. So the results basically showing that, well, for this 50 layers, um, the AMC actually find like this layer, let's say like this layer 8 probably. For layer 8, it learns that it's most of them are 3 by 3 convolutions. Okay? And then like the AMC find out, oh, for 3 by 3 convolutions, they'll actually have more redundancy. Therefore, we can prune more. Okay? So we can prune more. And at this point, like which is layer, let's say 12. Okay. So for layer 12, the AMC algorithm finds out, well, for layer 12, most of them actually are one by one um, kernels. So therefore, like it can has less redundancy and it can be pruned less. So basically, you can find that like they automatically learn which layer should be pruned more, which layer should be pruned less. And this one shows the experiments compare the comparison is made by MC with the baseline 1.0 mobile net and 0.75 mobile net. We can see that like this is the baseline, the original mobile net. You can see that like the accurate top one accuracy is 70%, 70.6, and with AMC it's pretty much maintained very similar and achieve like almost twice of speed up. So net adapt is another method based on iterative progressive method for layer pruning. It's also like aiming at pruning the finding the best pruning ratio for each layer in this whole network. The process is done iteratively. So let me show you how it works. So with the original model, the for each iteration, the algorithm is going to say, well, say like if the, I'm sorry, so it says like use latency string as an example. So let's say, well, this is the original network. I want to prune the network such that the latency is reduced by 100 milliseconds. Okay, let me do this. So I want to reduce the latency to 100 by 100 milliseconds. And what should I do? So what the algorithm does is that it's pruning the layers um, bit by bit, okay, and going through many layers. And every time I'm not going to, just say I'm going to prune one layer for 100 milliseconds. I'm going to use this so-called delta R, a certain amount, let's say like 5 milliseconds. Okay, so like this is manually defined. So what the question I'm asking in the first step is, well, with the original model, for this first layer, what should I prune? How should I prune it to reduce the total latency by 5 milliseconds? Okay, so you will find, oh, I can prune this way, or this way, or this way. So these three pruning are all for the first layer, but three different methods. All of them are going to give you 5 millisecond latency reduction. Okay, so that's fine. And then like for the second layer, I find, oh, I prune this way, I can achieve 5% reduction. And for the final layer, I prune in this way, I can get 5 millisecond reduction. Okay, now I have a lot of candidates, right? After I got all these pruning candidates for each particular layer, I'm going to do a short-term, just a very small fine-tuning and to get the accuracy for all these candidates. And then like out of all these candidates, I'm going to find the highest accuracy. Okay, oh, happen to be accuracy. Therefore, in this iteration, I'm going to say, oh, I am going to prune the first layer in this with this pruning method, while compare the other two, like this way of pruning, and this one can give me 5 milliseconds of latency reduction, okay, and give me this accuracy C. The second iteration, I'm going to repeat this whole process, and then I'm going to repeat it. Well, which layer should I prune and how should I prune it? Give me another 5 millisecond of reduction. Then you are going through this process again. You are going to do the short-term, fine tune again, and then you find one candidate again. So in this way, you are kind of like each step you trying to find the one layer to prune and to what ratio. Okay. And then you are going to do this over and over again until you reach to 100 milliseconds. So in our particular example, we are going to do this 20 times, right? So 20 times will give you, and each step is 5 milliseconds. So therefore, like totally, we are going to get 20 times the iteration and find one candidate that has the each layer got pruned. And finally, we are going to give this final candidate a long-term fine-tuning, trying to save the accuracy, to bring the accuracy back, to recover the accuracy. So that's this network adapt method. It's a little bit different from the reinforcement learning based method, right? So this is more like just try and error. So the way that it does with this iterative nature allow us to obtain a series of model with different cost because like we're going through so many like 20 iterations and that in the middle of it you can like get a lot of versions. Give me 1 sec. Okay. Um. So far we talked about what is pruning, the granularity, what are the criteria. The granularity is about the should we just arbitrary um, pruning pattern based, kernel based, or like channel based. Pruning criteria we talk about which nodes or which weights should be pruned. We talk about magnitude based method or second order based or like scaling factor based method. Then we talk about the pruning ratio. We talk about reinforcement learning based method. We talk about this net adapt. So finally, we are going to talk about this fine tune and train this prune network. So how do we improve the performance of the prune model? Because after pruning, usually we need to do fine tuning to recover the accuracy, and it does help to recover the accuracy. Um, this one shows after the pruning, the model accuracy will decrease. The fine tuning usually use a much smaller learning rate. Usually it's 1/100th or 1/10th of the original learning rate. This one should give you the example. If you just do the pruning, you have this accuracy drop. But after do the pruning and you fine tune it, you are going to recover some of the accuracy. And well, if we have this, can we repeat this process? The answer is yes. So we can, you know, repeat this whole process to, iteratively pruning and fine tuning to finally get this result. There's another thing I want to mention is this regularization. So when training the network for fine tuning, we can add this regularization term to the loss function to penalize non-zero parameter and encourage a smaller parameter. Let's see what that is. So the first method is this L1 regularization. So what it is that for the loss function, we are adding, this hyperparameter here plus the L1 norm of the weight. So the L1 norm essentially is the absolute value of the weight, right? So if you want to minimize the loss function, essentially you are going to you have to minimize both. So therefore, it's encouraging you to minimize the particular weights, okay? And well, the absolute value of the weights, and therefore, like it's encouraging you to it's a penalized non-zero parameter, and they want you push all the weights as close to zero as possible. So that's the L1 regularization. The L2 regularization essentially is calculating this square root of the square of these parameters. Um, so um, so also like both methods are going to encourage you to to minimize the loss, but also minimize the weight. So to keep them small so that it's easier to prune. So for example, like in magnitude based fine-tuning pruning method, they are going to apply a L2 regularization methods on the weight. So in if because it's a magnitude-based pruning method, if you are encouraging them to be as small as possible, then like the not important ones are going to be small to be easily to be pruned. Network slimming applied this smooth L1 regularization on this channel scaling factor. That's just different ways of using this regularization term to encourage, smaller parameter and penalize non-zero parameters. Okay, so now that leads us to the final topic of today's lecture. This lottery ticket hypothesis. This is actually I think it's the best paper in it won the best paper award in 2019 I conference. So what it says is that well for a so what is a lottery ticket? But what it says is that while a randomly initialized dense network contains a subnetwork that is initialized such that when trained in isolation, it can match the test accuracy of the original network after training for at most the same number of iterations. What does that mean? Let me see if I have a no. Okay. So what that means is that wow, if I have a dense network, and let me see just all these connections. Okay. So I have a dense network, and the hypothesis says, well, for this dense network, there exists a subnetwork, which is like this. Okay, which is a subnetwork after you somehow prune it. There exists such a network, and if both of them are initialized randomly, with all these weights are initial randomly, and I train this subnetwork T epochs. And if I train the dense network, also T epochs, the accuracy is going to be the same. Does that make sense? And they are trained in isolation. Um, they are going to have you can achieve the. So basically, it says for any dense network, I can find a subnetwork and train at the most the same number of epochs. I will achieve the same accuracy. The question is, how do I find this? So we call this, this subnetwork a winning ticket or lottery ticket. The question is, how do I find this lottery ticket? So the method is this. So that's interesting, right? So the method is for this dense network, I'm going to train this, okay, dense network. Just train it normally. And then like I'm just going to prune these unimportant weights, okay? And use whatever pruning method you want to use. That's fine. But once you prune the network, once you prune this whole network, you got this structure. You reset, and you reset, you reset all the weights back to exact the same as the original weight. So basically, I keep the structure, but I'm going to discard all these weights, and I'm going to copy the weights from the original network. Does that make sense?
Yeah.
And then, based on this, I'm going to train the network and then keep pruning it and doing this iteratively until it stabilizes. until it stabilizes. And that network can achieve the same accuracy as the original accuracy if you train them the same number of epoch. So that's how it works. Um, so this whole iterative training process, this so-called IMP, this iterative magnitude pruning. So it's based on magnitude pruning. I'm sorry. So it's based on magnitude pruning. So this IMP process, if you keep doing this, and you are until it stabilizes, you are going to find this lottery ticket, and that's wonderful, right? So, but this training process usually takes a long time. Time equals money, and literally, it takes a lot of server time to train this. And then, like, what's if you have to go through all this training process? What's the point to find this? What's the significance of this lottery ticket, right? So the significance is that the lottery ticket can be transferred. What that means is that if I use the classification task to prune this dense network and find the lottery ticket, which is the subnetwork, okay? And this ticket, I can reuse this for another task, say detection and the segmentation. So basically says, well, once I use the classification task to find the lottery ticket can be easily transferred running, just tuning for detection and segmentation tasks. Okay, so what that means is that once I find one ticket, I can transfer this to a lot of other tasks, and that is the significance of this ticket. The question, so can a lottery ticket universally transfer to all downstream tasks the same well? If yes, the extraordinary cost of finding sparse mask can be amortized by reusing, right? So they find out yes. The iterative magnitude pruning can find you a good mask on the pre-trained models, no matter if it's supervised or unsupervised. And in NLPs, computer vision, even multimodality models, so the sparse subnetwork is transferable. Okay, so that's the significance. So Harsh is asking, can you determine the best case without this extensive pruning? You're asking about this lottery ticket, right? So hold on to your question, and we are going to answer that. So that's exactly the question that people are asking, and then like they start to research this this problem, and they find the answer. So let's I will get to that soon. So so people find out wow, apparently people ask us the same question as what Harsh did. How can I easily find this ticket? And people find that first of all, transferability. I apparently for transferability you want the better. Well, you want a better transferability, right? Means that like once I find it, I can apply to many different tasks. So people find that if you prune from a larger pre-trained model, it can produce a better transferable sparse network. So for example, if you prune from this ResNet 152, the transferability is better than this if you prune this from network 50. And then like people ask, is our transferable sparsity special? Means that is this like subnetwork a unique subnetwork? The answer is yes. So what they did is this. They compare, well, again, the x-axis is the remaining weight. The y-axis is the accuracy. Okay. And while for the orange line, it's the one that with the ticket we find. Okay. the ticket we find. The blue line, I'm sorry. Oh, the blue line is a random pruned network, which has the same sparsity. So you can see that for any particular sparsity, the blue line is significantly less. So what they did is one more experiments is that for 10% of the weight, the already, the in the winning lottery ticket, in the lottery ticket, I randomly pick 10% of the weights and I just flip it. Okay. And end up like you can see that only flip 10% of accuracy. The lottery ticket start to so it's kind of like we are adding the turbulent the turbulence to the weight only 10%, and you can see the accuracy start to drop. So this lottery ticket is unique. So so people trying to kind of like trying to understand like why the transferability, why there is a lottery ticket. This is an analogy. This is analogy with this physics system. You don't really need to fully understand this, but the general idea is that in physics we have this renormalization group operation. If you just look at this, this kind of barcode, it's kind of this coerced graining process in a system. What that means is that like this one give you a high resolution, right? This one kind of give you this coerced version or this lower resolution of the image. But this one kind of like give you the general idea of this white pattern here. Okay, and you can see that this white pattern here. Okay, so basically we are extracting what are the higher level, what are the high level important information in this pattern while ignoring all these low level details. That's this coercing process does. And and people find that like when we are searching the lottery ticket, it's a very similar process with this this fully connected layer to this is kind of like this coercing process. So this promise a bring a promising paradigm for the foundation models, right? Like large language models, the ChatGPT, Google Gemini. Instead of like using this dense, gigantic pre-training model, what we can do is that we pre-train a large model, and we find it's a sparse lottery, and we deploy and transfer, right? So that's the the ideal situation. So soon later, people find an interesting thing that if the network is wide enough, a random pool spots actually is going to match the dense. What that means is that this WRN50 is this wide ResNet 50. When we say like wide, usually it has a parameter of k. For example, if it's k is 2, means that like the wide ResNet has the twice of the width of the original ResNet 50. Okay, so for example, for a wide ResNet 50, you just randomly prune them to 50% of the network. It can actually achieve. It's going to be the lottery ticket. So there are going to be a lot of different lottery tickets. Basically says there are a lot of good tickets for a wide network. Another question people asking is that, well, with lottery ticket, then while you are pruning, like, can you actually achieve this wall clock time saving? And of course, like with this, very because if you look at the pruning pattern here, this is a pretty much irregular pruning, right? This is an irregular pruning, and people propose some of these, grouping method with of course, you need an index matrix to indicate like where they were. So with this kind of a method, people can still achieve like 60, 50, 65% time clock saving on ImageNet. I forgot which network it is. But yes, lottery ticket can give you this very good sparsity, achieve the same accuracy as the original dense network, still can achieve actual speed up. So robustness, let me skip this. So to answer Harsh's question, is this paper called Early Bird Lottery Ticket. So what the people find out is that when you are doing this iterative process, when you are find this iterative doing this iterative process, in many cases, the lottery ticket actually emerge very early stage. You don't need to, train all the way until the network totally stabilized. Means that you can't prune anymore. Okay, um, so they find out like in the early stage, once you can see that the network doesn't, they set a threshold. As soon as the pruning does not change the network as much, then they just stop. And they prove that like with this early bird lottery ticket, they can achieve like just a very small accuracy sacrifice compared with the original dense network. So this is their experiments. Um, so this, if you are interested, you can find this paper, this sparsity win twice. Um, so I'm going to skip the robustness. So this is security. I'm going to also skip the security part. Oh, this one just give you, so that pretty much covers the whole, pruning class, but this one give you, a little bit more because, um, I know some of you might come from a very hardware background. So, I want to talk a little bit about, this system support for sparsity. So, particularly, I want to talk about this EIE paper and this NVIDIA Tensor Core. I briefly talked about this earlier, right? So the EIE engine, this efficient inference engine, what it does essentially says, well, after the pruning, I find out that um, most of the static weight, I'm sorry, the static sparsity. The static sparsity refers to the weight. So the weight after we prune it, a lot of weight got pruned, right? So they are all zeros. And when you are multiply zero with the activation value, it's going to be zero. In traditional computer processor, they are going, even though it's zero, they are going to calculate it. So they propose, the hardware that, once you detect a zero, it's going to skip this multiplication for weights, or this so-called static sparsity. And this dynamic sparsity essentially says, well, if the activation after the rerule is zero, which says like 90% of them are zeros, then also it's going to detect that part and going to skip the calculation to multiply the weight with the activation value. So that's two part. The third innovation in this paper says I'm going to do some weight sharing. So basically, it's maintaining a lookup table. And if some of the weights are already present in the memory, I'm just going to store a index instead of the original weight. So by doing this so-called weight sharing, they can save more memory access. So basically, this engine, three innovations: detect the zeros in the weight, detect the zeros in the activation after relu function, and then like share the weight. This one give you the detailed calculation, just show you the data flow, and they compare, their design with CPU, GPU, and this Jetson TK1, which is the, this 28 nanometer ASIC, and they find out, they can improve the throughput. This is the energy efficiency, which is the higher the better. So the NVIDIA Tensor Core, which one is supports this MN or NM or MN with sparsity. So far, I think it's 800 supports this 2.4 sparsity. Let me go to this one. Okay, so this is the original one. This is the new design to support the sparsity. The key idea is that um, the key idea is that uh, for the non-zero weight, see, you are compressing the weight by half, but you also have a two-bit indices, right? So the hardware now like needs the hardware now instead of just grabbing the data from the matrix, now need to from the index and the weight need to recover, what results to be used here and to multiply with original. So the this matrix and this matrix, the red matrix and the yellow matrix remains the same. The only difference is this green and this purple one. And essentially, we got this green part and the purple part, and the purple part is using to find the index and to calculate with this. So that's the main innovation. It's quite simple actually. So essentially, this is a selector and this is a mux, right? So you are selecting, in order to multiply, for example, with this green element, which element from the red one should I use, basically. So that's a experiment. That's the experiment results. And pretty much they all maintaining accuracy and achieve 2 times speed up. All right. So that's all I want to cover for today's lecture. Any questions, comments, concerns? So we are going to release, lab one soon. So please pay attention. I will send out a email. There is a lab zero, which is kind of a tutorial, very easy step-by-step tutorial. So if you are not familiar with the collab environment, you probably want to go through the lab zero. But if you are very familiar with it, it's not necessary. Okay, so that's all for today's class. If you don't have any questions, you can leave now. If you have any questions, you can stay and ask.
What will
Thank you,
lab one
Professor.
be about?
Yeah,
Thank you, Professor.
of course.
Excuse me, Professor.
Yes.
So, like, when are we going to get the recorded video?
Um, so it depends on when Zoom will generate the video. So once they generate, I will release the video.
Got you. Thank you, Professor.
Okay. Yeah. What do we go? So you are going to learn about, this is sparsity, how to do the pruning and measure, the performance after the pruning.